Okay, the theorem of absolute convergence. So if a series, which is the sum of the terms of an from n equals 1 to infinity, is absolutely convergent, then it is convergent. So absolutely convergent just means if we take the absolute value of the series and show that that converges. So instead of an, we take the absolute value of an. And just see if that converges. Here we have the sum from n equals 1 to infinity of cos n over n squared. So what we're going to do to show it's absolutely convergent, we're going to consider this series. So the series from n equals 1 to infinity of the absolute value of this. And see if we can show that that converges. And it's a lot easier to do. Do note that just because, so if we show that something is absolutely convergent, then it shows that it's convergent. This rule does not work both ways around. If something is convergent, it does not mean that it's absolutely convergent. It often will be, but it won't always be. So now to start this off, we know a little bit about cos n. So when you consider cos n as an actual sequence, you think cos n fluctuates between a maximum of 1 and a minimum of -1. Some terms are positive and some are negative, but it certainly doesn't go positive, negative, positive, negative. So it's not an alternating series. Okay, if you think about cos n, one thing you should definitely know is that the absolute value of cos n has a maximum of 1, so it's always less than or equal to 1. So now we're looking to get a situation where we can use a comparison test. So the absolute value of cos n over n squared must be less than or equal to 1 over n squared. Now, if you think about this, because remember, we're trying to turn this into the absolute value of cos n over n squared. But if you just think about n squared, well, it's going to be positive anyway. I mean, n is always positive for a series. So n squared is definitely going to be positive. So actually, it's completely equivalent to say cos n, the absolute value of cos n over n squared is exactly the same as cos n over n squared, and the absolute value of all of it as n squared is always greater than or equal to 0. So it's no issue. It doesn't have any effect on the sign. So now we can say that the absolute value of cos n over n squared, we know is less than or equal to 1 over n squared, and we know it is always going to be greater than or equal to 0. Because we know we can't have any negative terms for various reasons, really. Firstly, because it's an absolute value thing. Secondly, because we know that n squared is non-negative anyway. So now we're in a condition where we can apply the comparison test. So basically, we're going to look at the series from n equals 1 to infinity of 1 over n squared. And we know this converges because it is a p series with p greater than 1. And it converges because it is a p series with p greater than 1. So if we know that that series converges, well, the series from n equals 1 to infinity of the absolute value of cos n over n squared must also converge, also converges. And this is because of a comparison test. Remember, we got it trapped between a sequence that we knew for the domain, the natural domain, as in a positive integer n, was greater than it, and we knew that everything was positive. So that is comparison test. So we are nearly there. If we just go back and think of what we're actually trying to show. So we are trying to show that this series converges. We have now shown that the absolute value of that series converges, and the theorem of absolute convergence shows us that if a series is absolutely convergent, e.g. if the series of the absolute value of the terms in the sequence converges, then the actual series must converge as well. So to finish off, the series from n equals 1 to infinity of cos n over n squared is absolutely convergent and hence convergent. And the reason for that is the theorem of absolute convergence.